Now that we know some things about how to differentiate rational functions, let's try and differentiate some functions and get the hang of it. So these were the rules that we just learned, and they just say that, hey, if you have a rational power, let's just treat it like an integer. Let's just apply the same rules, bring the power in the front, and then subtract one out of it. And let's apply these rules. So let's start with a pretty elementary rational power. Let's say we want to differentiate z equals the square root of x. Now, before I even go to differentiate this function, it would be a nice exercise to check at what values of x a function is defined or not, since in rational powers it's more often the case that at some points the function that you get is not defined. So the square root of x, we know that square root of negative numbers, let's say the square root of -1, this does not make any sense. At least it does not make any sense in the real numbers. This is a complex number, by the way. And thus the only values for which z is defined are values when x is greater than or equal to 0. Now, if you want to differentiate this, well, we can write dz over dx as d over dx of x to the power of half. Now, instead of having p over q here, you now have half. So we will take all of this, bring it to the front. So we will have half times x to the power half minus 1. And this gives you 1 over 2 times x to the power of negative half, or this is just a square root with a negative power, so you will just bring all of that into the denominator. This is the derivative of square root of x. At the same time, it might be worthwhile to notice that if you have x equals 0 here, this just brings this denominator to be equal to 0, and 1 over 0 does not make any sense. So what we can say, hey, well, this derivative is not defined for all values of x as well. It's only defined for x greater than 0. Let's look at some more functions. So let's think about a function defined by y equals sine of x to the power 100 over 91. And I just chose a random power right here. It does not signify anything. And here you don't have a simple x to the power of something, x to the power of p over q, but instead we have a function instead of x. So what do we do if we have a function instead of x? Well, we apply the chain rule. So dy over dx is equal to d over dx of the sine of x to the power 100 over 91. Now, we have to replace sine of x by something just to apply the chain rule. So let's say that sine of x is equal to u. Let's say u is equal to sine of x. So this you can now write as d over du of u to the power of 100 over 91. That's what this will become, multiplied by the derivative of du with respect to x. Now, this 100 over 91 is a rational power. Bring it here, subtract 1 in the power itself. So we will have 100 over 91 times u to the power of 100 over 91 minus 1. All of this being multiplied by the derivative of sine of x. So the derivative of sine of x is cos of x. And instead of u, we will just write, well, the sine of x. That's what the substitution is. So this will be equal to 100 over 91 times sine of x to the power. So we have 100 over 91 minus 1, and that's just equal to 9 over 91, just basic arithmetic. And this is being multiplied by the cos of x. If you want to check the domain of this function, well, sine of x and cos of x are pretty smooth functions. They are defined on all real numbers, and thus this derivative as well as this function, both of these will exist for all real values of x. Let's look at one more function before we end this video. So let's think about y equals 1 minus x squared to the power negative half. Now, this here again is a function embedded inside a rational power. So the best way to do this, from my perspective, will be to just use the chain rule. So let me just write the substitution beforehand. So let's use v equals 1 minus x squared. So this function actually becomes y equals v to the power of negative half. Now, dy over dx is equal to dy over dv times dv over dx. That would be the derivative, but we'll come to that later. Just for a second, let's just look at where this function is defined. So this function is defined, let me just write it in a better way. This will look like 1 over the square root of 1 minus x squared. This function is defined whenever this square root is defined and is not equal to 0. If the square root is equal to 0, 1 over 0 does not make any sense. And we cannot let this number 1 minus x squared to be negative as well. This also cannot be allowed in the real numbers. So the this is not allowed. Let me just write that down, not allowed. So the only cases wherein this will be allowed, wherein this function will be computable, is when 1 minus x squared is greater than 0. And this happens, if you just check it, this happens in the case when x belongs to -1 to 1, not including -1 and 1. Now, if you want to, let's say, start and differentiate this function, you can write dy over dv as negative half v to the power of -3 halves. And the reason why I did that is very straightforward. I took this -1 half, brought it here, and subtracted 1 out of it. And then dv over dx, the derivative of 1 minus x squared, this you can write, let me just do this one right here. This will be d over dx of 1 minus d over dx of x squared. The derivative of 1 is just equal to 0, minus the derivative of x squared is equal to 2x. Now, you will have negative half v to the power of -3 halves multiplied by -2x. Negative signs cancel out. These 2's cancel out. And you're left with x multiplied by, instead of v, let's just write with the substitution that we had. So 1 minus x squared to the power of -3 halves. This is the derivative. Now, if you just want to check wherever this derivative is defined, this derivative can be written as x over 1 minus x squared times the square root of 1 minus x, right? Because 3 halves can be written as 1 plus half, and I just did that just to make it look a bit cleaner. Now, we know that this thing cannot be negative, 1 minus x squared, even though it occurs in both places. This cannot be negative, so 1 minus x squared has to be greater than 0 or equal to it. But at the same time, if 1 minus x squared is equal to 0, this denominator goes to be equal to 0, and again, the function does not make any sense. So 1 minus x squared has to be strictly greater than 0 in order for this derivative to be defined. And this is the same criteria that we derived before. So this means that x will belong to -1 to 1, excluding both of them. And so perhaps this gives you a bit of an intuition of the fact that rational powers are just like integer powers. They in fact don't even have a lot of new concepts involved in them, and they're pretty easy. See you in the next video.